Hello, this is Jack Jackson. We're back with going through the solutions to the review problems from Unit 1 on limits and continuity. So which of the following classes of functions consist entirely of continuous functions? Circle all that apply. Polynomial functions, a sine and cosine function, are all continuous functions. In fact, they have the domain of all real numbers, in fact. All of the others are continuous where they're defined, but they may have places where they're undefined. Rational functions, actually some rational functions, including polynomials and some non-polynomial functions, are continuous, but other rational functions are not. Rational functions can have holes in the graph or vertical asymptotes, places where they're undefined that give us breaks, discontinuities. Tangent and secant functions both have infinitely many discontinuities, vertical asymptotes there. The rational functions only have a finite number of discontinuities, places that make the denominator 0. Power functions, it depends on what the power is. Some power functions are continuous functions, but there are some, particularly the negative power functions, have vertical negative power functions have vertical asymptotes, and the zero power function has a hole in the graph. Okay. Functions with a constant rate of change are linear functions. In fact, that's if you really only know one thing about linear functions besides maybe the graph is a line, you should remember that. That's the most important thing about them. In fact, that constant rate of change is what makes them straight. Here are some of the different forms of the equation that are pretty good to use. The point slope form is f of x equals m parentheses x minus x1, close parentheses, plus y1, where x1, y1 is the point on graph and m is the slope. If you specifically put in 0, y sub 0, which is the y-intercept, then this reduces to f of x equals mx plus y sub 0. You might have known as mx plus b. That's m is the slope and y is, sub 0 is the y-coordinate of the y-intercept. And that's the slope y-intercept form, or just the slope-intercept form. There's also a slope-x-intercept form that's the factored form. F of x is m times parentheses x minus x sub 0, and here x sub 0 comma 0 is the x-intercept. M is the slope. The slope m is delta y over delta x, y2 minus y1 over x2 minus x1, y2 minus y1 over x2 minus x1. That is the slope. The constant rate of change between any 2 points. We can do this between any 2 points on any function, but if it always turns out to be the same thing every time, that's what makes it linear. Compare and contrast that with exponential functions, which have a constant relative rate of change, a constant percentage change. So linear functions, the amount of change each time, each unit of time, or each unit of the input is going to be the same amount of change, but not necessarily the same percentage change. It's backwards for this. Exponential functions have the same percentage change, but not the same actual rate of change. We get similar formulas. F of x equals y sub 0 b to the x power. B is the base, which is y2 divided by 1, y1 to the power of 1 over delta x. And if you notice that this is very similar to what we had up here for linear functions, it's just one level higher in the order of operations. This is kind of like the base y-intercept form. And the base is here is kind of like the slope up here, but instead of multiplication here, this becomes a power. And instead of multiplication here, it is a sum up here. Everything's one level higher in the order of operations here. And just like there's a point slope form here, there's a point base form down here and so forth. But I didn't go over those. Now, thinking back to the definition of the limit, let's go back over that real fast. The definition of the limit says here, given a function f and a real number constant c and l, we say the limit is x goes to c of f of x is l if and only if for any epsilon greater than 0 there exists a delta greater than 0 such that if c minus x is less than x, c minus delta is less than x, which is less than c plus delta, but x is not c, then L minus epsilon is less than f of x, which is less than L plus epsilon. So notice that epsilon and delta serve a specific role in this definition, and we want certain inequalities to be true, those there. So this down here, this question is working with that. So here we know what the limit of this function is. We know what the thing we're trying to approach. C is 4. The L is 41. Here's our f of x. We're given an epsilon. What is an appropriate delta to go with that? Well, let's find that. So here we can take the formula, which we can put in here. We put the limit plus epsilon and limit minus epsilon gives us horizontal lines. And what we really want to do is find those two places of intersection, which we could solve using the quadratic formula, because this cancels out. Do 3x squared minus 7 equals that number, and 3x squared minus 7 equals that. But we can also do it with technology by just calculating the intersection of those 2 points. And we get the x values there. And this one is going to be the 4 minus delta. Okay, is going to be the one on the, let's see. So 4 minus delta is here. And so we can work that out. Okay. And so solving that 4 minus that x value is going to give us delta. And then similarly over here, this is 4 plus delta, so solving at x minus 4 will give us delta. Now what we want is the smaller of these two deltas. Since this is this is a quadratic, these are actually a little bit different, not too far off. But we take the smaller of these two, looks like that's the one on the right. And this is going to be the delta we use. And it says approximate that to 5 decimal places. That's a 5 in that place. We can see that that works out because since it just said find the thing, we could stop there. But if we want to see why that works, we can verify if we weren't supposed to verify the inequalities, we want to show that f of x, when it's between L minus epsilon and L plus epsilon, that's going to happen, that is going to happen whenever we get x between here and here. So if this is epsilon here, we want to show that this is true. To show that's true, we want to add, let's see, well, I just went ahead and added those together. We want to show that this function is between there and there. The x minus 4s are going to cancel out, because remember, we're not letting x be 4. Here we add 7 to all 3 sides, divide by 3, and then take a square root. So x is less than the minimum of these two things, which is here. Okay, and then the absolute value of x minus 4 is this, which works out to be approximately this for delta. Four zeros and a 4. Notice that the times 10 to the negative 5th here, so that's 4 zeros, then a 4, 1, 6, 6, 6, 5 if we went out that way. But to 5 decimal places, it's 4 zeros and then a 4. This one does a similar thing, but epsilon is a variable. Give delta as a function of epsilon. This one again reduces as x plus 4 times x minus 4 over x minus 4. Those cancels, reduces to x plus 4. C is not 4. It's a linear function. For linear functions, if we just let delta be epsilon over m, this always works out. So delta and epsilon are the same for that one. Again, you could go through a process such as this right here and see that it works as well. All right, next question. Evaluate some limits here and use some of the algebraic shortcuts that we know. Well, one of the things that we studied was we're taking limits as x goes to infinity or negative infinity. For a rational function like this, we could just take the leading terms here, ignore the rest. That reduces to this power function, 6/5 times x to the negative 2. And we know that as x goes to negative infinity, that goes to 0. So anytime the power, or in other words, anytime the power is bigger in the denominator than it is in the numerator, it's going to have a horizontal asymptote of the x-axis on both ends. Okay, and this one, the trick, algebraic trick that we do, or algebraic technique that we apply, is we need to rationalize the numerator by multiplying by the conjugate. So we take the same thing with the plus here, and we multiply that by the top and by the bottom. And the top, this gives us a sum and difference pattern, which is a difference of two squares. So it's the first term squared, which just takes away the square root, minus the second term squared, again taking away the square root. Leave the bottom like it is. Distribute this minus, and then combine like terms, we get 2x here. The x's can be canceled out. They're not 0. They're only getting close to 0. And so we get this. Now at this point, this is continuous function, so we can just plug in 0 for the x's. And let's see, what do we get? 1 plus 0 is 1. Square root of that's 1 here and here. 1 plus 1 is 2. 2 divided by 2 is 1. So that limit is 1. Now, you could verify that by, and you are encouraged to do so, by looking at a graph and a table. And what we should see on the graph is approaching the point 0, 1 as being a hole in the graph. You can see that in the table. Up here, this is the horizontal asymptotes on both ends is 0 to see that one. Here we notice that sine of 2x over x squared, we're going to see that the answer is 0 here, but we're going to use the Squeeze Theorem. Sine of 2x is between negative 1 and 1. Sine of anything is between negative 1 and 1, inclusive. Multiply both sides by x squared, which is a positive number, so we get minus 1 over x squared is less than or equal to, multiply all three sides by 1 over x squared, I should say. And so we get negative 1 over x squared is less than or equal to sine of 2x over x squared, which is less than or equal to 1 over x squared. And we know that the limits, as x goes to infinity, if these are in order like this, the limits have to be in order. Had these been any less thans, these would still be less than or equal to's here. And we know that both these on the ends go to 0, so by the Squeeze Theorem, this has to be 0 as well. Okay, consider this class of functions. F of x equals x to the p over q, where p and q are constants, with the greatest common divisor, p and q equals 1. In other words, that fraction p over q is reduced. This is a class of functions called power functions. We also have power functions. We have a x to a irrational power as well. So these functions have a variable base and a constant power. They always have a part that's in quadrant 1 and go through the point 1, 1. 1 to any power is 1. And what happens beyond that depends a little bit about the values of p and q and the size of p over q. So what happens in quadrant 1 depends on the size of p over q. If p over q is negative, we have decreasing concave up, that should say. If the power is 0, we have a constant function, y equals 1 in the first quadrant. Actually, it's y equals 1 everywhere, except it has a hole in the graph at 0, 1. If the p is between 0 and 1, we are increasing but concave down. If p over q is, that's supposed to say 1, it's increasing linear. And if p over q is greater than 1, it's increasing concave up. What happens to the rest? Now that's just describing the first quadrant graph. Let me be sure this describes. Quadrant 1 only, so make sure we're very, very clear about that. Okay. Now, what happens to the rest of the graph? Well, it depends on whether p and q are even or odd. If p is even and q is odd, even, so it's basically an even power and an odd root, it's going to have y-axis symmetry and be in quadrants 1 and 2. If P and Q are both odd, it has origin symmetry in its quadrants 1 and 3. If P is odd and Q is even, it doesn't have any symmetry and it's only in quadrant 1. And those P and Q can't both be even because we said that they have to be reduced fraction. So this section we have to come up with formulas for functions with certain characteristics. The graph goes through the point 250 and it has a constant relative rate of change 2%. Well, that right there tells you it has to be exponential. And there's only one possible function. It's here, the base is 1.02, 1 plus the rate of change in decimal form. And then this is sort of the point base formula, x minus the x value here for the power, and the base is the y value of that point is right here. So notice if you plug in x is 2, the power is 0, so that becomes 1 times 50 is 50. If you want to rewrite it with just an x up here, then this becomes 1.02 to the x times 1.02 to the negative 2, which I could write down here, or approximately this. This one goes through the point 27, has a constant rate of change, not relative rate, not percentage change, but actual rate of change. That's a constant slope. That's a linear function. So here's the point slope formula. 2/3 is the slope times x minus 2, x minus the x coordinate, and then plus the y coordinate. Notice where we have multiplication here, we have addition here. Where we have multiplication here, we have a power here. The power here is like this here. It's x minus the x coordinate. And the plus here is like the times here. That's the y coordinate. So everything is one level higher for the exponential than it is for the linear. A function g has a hole at x equals 3, but it's continuous everywhere. So notice a and b, there were only one possible function. This time there are infinitely many. One of the easiest ones would be just x times x minus 3 over x minus 3. That's just like y equals x, but then with a hole at 3. The function is rational with the limit as x goes to minus infinity is 5. F is equals 3 and a hole at 2. There are actually many possible functions, but the one that has the smallest degree, or one of them, would look something like this. Basically, you leave off the x minus 2 for a minute. It has a vertical asymptote at x equals 4, so you need an x minus 4 in the denominator. It needs to have a leading coefficient of 5 for the horizontal asymptote to be 5. And then if we plug in 3, we need to get, plug in 0, we need to get 3. So that's whatever this number is over negative 4 needs to be 3, so that needs to make that negative 12. Then you plug the hole in it, punch the hole in it by multiplying the top and bottom by x minus 2. And I believe that one will work out. And there's other options, but you're always going to have this factor of x minus 2 here that cancels. You have the x minus 4 here and no other factors in the denominator. And this needs to be something like similar to this. A function is continuous, concave down, and increasing. There's many possibilities. One would be a logarithm function. Another one would be like a square root function, or certain power functions would look like that as well. Notice it did not say the domain had to be all real numbers. Function is a power function which has y-axis symmetry and is increasing in the first quadrant. So increasing in the first quadrant means we need a positive power, and y-axis symmetry, we need p over q, where p is even and q is odd. So say x to the 2/3 would be one example. There's lots of others. All right, let's see. This one here, we want to look at this table. Here, quit moving around on me. Okay. Okay, so here we're given the table, the black numbers here. X is on the top, Y is on the bottom. And notice that delta X is 6, 12, 12, and 12. But if we do delta Y over delta X every time, we can figure the delta Y here. It's -4, it's -8, all these. So -8 divided by 12 or -4 divided by 6 reduces to -2/3. That's a constant slope between successive points in every pair. So that means this is a linear function, and that's the slope. Pick a point that we want. Looks like the easiest looking one is 3, 2, and do x minus the x coordinate 3 times the slope plus the y coordinate, or if you'd like slope-intercept form better, distribute and combine like terms. -2/3 x plus 4 would be our function. So that looks like it's linear. This one down here is exponential. Delta x is 2, 4, 2, 4. But here what I'm going to do is not subtract the y's, which is clearly different, but I'm going to divide. And here I get 9, 81, 9, and 81, which at least approximately, some of these values have been rounded off in the table, so at least you get approximately those values. And then the base being the y2 divided by y1 to the power 1 over delta x. So we do 9 to the 1/2 power is 3, 81 to the 1/4 power is 3, and repeat those values again. So that base is a constant. That's an exponential function. There's the base. And we can pick a point here, 218, put an 18 here, put x minus 2 in the power. Or this one reduces nicely to this, 2 times 3 to the x power. All right, let's look through these matching ones. Tell you what, let's call this video right now. We'll do that matching in the next video.